Hello, today's video is a pre-lab lecture for colligative properties, freezing point depression. Now, this lab has to do with colligative properties in aqueous solutions. So we just want to establish a baseline real quick to what actually is an aqueous solution and what components make up an aqueous solution. So aqueous solutions are formed by dissolving one or more chemicals in water. So aqua means water, so the aqueous, the aqua prefix for the aqueous word means a solution in water. And so our aqueous solution is composed of two different components, a solute and a solvent. So the solute is defined as the chemical that is being dissolved in a solution. The solvent is the chemical that you are dissolving in. And so for an aqueous solution, the solvent is always going to be water. And so whenever you're talking about dissolving a solute into a solvent, we have a term that's called like dissolves like. And so that saying indicates that polar solvents, so like dissolves like is talking about polarity. If you have a polar solvent, that will dissolve polar solutes. If you have a non-polar solvent, that will dissolve non-polar solutes. The opposites do not dissolve each other. Okay, so if we're talking about water as a solvent for aqueous solutions, water is polar. So that means only polar solutes are going to be able to be dissolved in aqueous solutions. Okay, so we can consider several different aqueous solutions. You could have sodium chloride, which is just table salt. That solid table salt, when you put it in water, will dissolve into Na plus and Cl minus ions. Na plus, aqueous, plus Cl minus, aqueous ions. Glucose, which is a small molecule, when you put that in solution, it's going to dissolve into just that glucose molecule in an aqueous state. Caffeine, for example, if you take solid caffeine, put it in water, that will dissolve into just aqueous caffeine. So you see that ionic solids will break apart into their individual ions, but molecules stay together and just change from solid into aqueous state. So let's think for a moment about how dissolving actually works. So dissolving of salts occurs due to ion dipole interactions. So if we think about a salt, so for example, sodium chloride here, we know that salts exist in this crystal lattice formation. And so that crystal lattice is being held together by our lattice energy, where our lattice energy is proportional to the charges on the cation and anion over the interatomic distance squared. So the higher the charges on those ions, the stronger the lattice energy, and then the smaller the individual molecules or individual ions, the stronger the lattice energy is going to be. So in order for that crystal lattice to come undone, to split into its individual ions, there needs to be a strong enough interaction between the solvent, the water, and those individual ions in order to overcome those Coulombic attractions and rip all those individual ions out. And so that occurs using this ion dipole interaction. So we know for water being a polar molecule, you have a dipole moment going straight upwards, where you have a partial negative charge on the oxygen and a partial positive charge on these hydrogens. And so you can have an interaction where the partially negative part of water will interact with the positive Na plus ions to form an ion dipole interaction strong enough to overcome this Coulombic force and rip it away. Whereas the partial positive side, by the hydrogens of water, will interact with our negatively charged Cl minus anion in order to overcome that Coulombic attraction and rip it off into a negatively charged ion. And so once those free ions are in solution, they become what's called hydrated, which means that you have several different water molecules that surround that individual ion in solution. Okay, and then so a salt dissolves because all of these water molecules are going to come in and rip apart all of these individual ions, so breaking apart the crystal lattice. And so once we create a solution, an aqueous solution, we have various different units to express the concentration of that solution. So concentration is essentially how much solute do you have per solvent. And so we already know about molarity. So molarity, big M, is moles of solute over liters of solution. We also have a unit of mole fraction, which tells you the mole ratio between our solute and solvent. You can have the mass percent, where you talk about the relative amounts of solute to solvent in grams. And then a new unit here that we're presenting to you called molality, which is lowercase m. Okay, so the mole fraction and mass percent we don't use a whole lot for aqueous solutions, so I wouldn't really worry about these two overly. Really just consider the molarity and molality. So molarity, big M, we've used that a lot this course already. Molality is sort of a new concept. So molality is defined as the moles of solute over kilograms of solvent. Okay, so the top moles of solute is the same in both situations, but instead of liters of solution for molarity, we have kilograms of solvent for molality. Okay, so what's the difference between the two? The difference between the two has to do with whether the measurement is temperature dependent or temperature independent. Okay, so if we think about the volume of a liquid, so let's consider that I have a 1 liter of water. And so this water is at room temperature at 25 degrees Celsius. Okay, so there's a certain number of H2O molecules that exist in this 1 liter of H2O liquid. Okay, so this is liquid at 25 degrees Celsius. So there's a fixed number of molecules there of water that compose that 1 liter of water at 25 degrees Celsius. If we start to heat that solution up, if our temperature goes up higher and higher and higher, and we're approaching our boiling point, say we get up to 90 degrees Celsius, we have the same number of molecules in this H2O, but they're moving much faster. And they're moving so much faster, we're going to start to see some expansion of that liquid. And so instead of it taking up 1 liter, possibly at 90 degrees Celsius, it'll take up, say, maybe 1.1 liters. The volume of that liquid depends on the temperature. Okay? If we were to lower that temperature of the water, we would see that the molecular speed is going to start to slow down and that volume is going to contract. So maybe if we take a look down at 5 degrees Celsius, maybe that volume will be 0.9 liters. So volume itself is temperature dependent. So therefore, since volume is a temperature dependent measurement, molarity itself is temperature dependent. Whereas molality, which we have moles of solute over kilograms of solvent, if we take the measurement of this amount of water, whether it's at 25 degrees, 90 degrees, or 5 degrees, we'll always have the identical mass. Because the mass, if we go back to the very beginning of this course, the mass tells us the amount of matter that we have. So the mass is a temperature independent value. So if we express concentration in terms of molality, then we are dealing with a temperature independent unit for concentration. And so when we're dealing with these colligative properties that we're introducing today, so changes in boiling and freezing points, we are altering temperatures. And whenever we're dealing with equations that alter temperatures, it's important that we express our units in a temperature independent manner, meaning that this molality concentration we're introducing in today's lecture becomes highly relevant. So again, molality is moles of solute over kilograms of solvent. Okay, so for aqueous solutions, it would be kilograms of water. Okay, so now that we've sort of introduced our aqueous solutions and solutes and solvents and units for measurement for those aqueous solutions, Now let's get to the concept of colligative properties. So it can be observed that dissolving a solute changes several properties of a solvent. And so this is a generalized term called colligative properties. So colligative properties are defined as properties that depend only on the amount of dissolved solute and not on the solute's chemical identity. And so vapor pressure, boiling point, freezing point, and osmotic pressure are all factors that are colligative properties that are altered by the amount of our dissolved solute in our solution. Okay, and so you're going to find in working through this lab, we all know in the wintertime, if you want to melt salt on the sidewalks, you put salt on the sidewalks. Why does that work? We're going to get to that in today's lab when we're getting towards understanding more about colligative properties, how putting in a dissolved solute in a solution will alter the freezing point through colligative properties. So in that definition, colligative properties state properties that depend only on the amount of dissolved solute and not on the solute's chemical identity. So what is meant by this term amount of dissolved solute? Okay, so colligative properties depend on the number of dissolved particles in solution. And so this term particles is very broad, meaning that it could talk about atoms, monoatomic ions, polyatomic ions, molecules. All of these count the same. They all would be one single particle. Okay? Whether it's a tiny little atom or a huge molecule, it counts as one particle. So if we think about dissolving several different solutions in aqueous solutions, let's consider how many particles that each of these individual materials break up into. So if we look at NaCl, when we put this solid into our aqueous solution, we get Na plus aqueous plus Cl minus aqueous. So we can see there's one Na plus and one Cl minus. There's a total of 2 particles that break up into solution. If we look at calcium chloride, this splits up into calcium 2 plus aqueous plus 2 Cl minus aqueous. So we have 1 plus 2. There are 3 particles that break into solution for calcium chloride. Glucose is not a salt, so it simply just goes from glucose solid to glucose aqueous. So there's only 1 particle. Caffeine, same thing, it's just a molecule. So we go from caffeine solid to caffeine aqueous. 1 particle. Okay, aluminum sulfate splits into 2Al3 plus 3 SO4, 2 minus. So there's 2 plus 3, there's 5 particles. So we can observe lots of different materials, how they break up into solution, they they produce different number of, quote, particles in solution. So for colligative properties that depend on the amount of particles in solution, we need to be able to quantify that amount of particles for any given substance that is dissolved in an aqueous solution. So here comes in the term the Van't Hoff factor. So the Van't Hoff factor, which has the symbol of I, quantifies the number of particles that a solute breaks into when you dissolve it in solution. So the Van't Hoff factor is given as the moles of particles in solution over the moles of solute dissolved. So if we assume here that if we dissolve 1 molarity, or 1 mole of our solute, this will tell you the number of moles of particles that they break up in solution. So basically, the same number that we just solved for back here are going to be our Van't Hoff factor I. So since NaCl breaks into Na plus and Cl minus, we have an I is equal to 2 because we broke up into 1, 2 particles. CaCl2 is going to have a Van't-Hoff factor of equal to 3 because you have 1 calcium, 2 chlorides, as in the previous slide. Glucose will have a Van't-Hoff factor equal to 1 because there's simply just one glucose that turns into aqueous. Caffeine, again, Van't-Hoff factor equal to 1. A new aluminum sulfate, Van't-Hoff factor of 5. 2 aluminums, 3 sulfates, gives us an I of 5. So the Van't-Hoff factor simply just tells you how many particles that a given solute breaks into. So now we can get to the colligative property equation for freezing point depression and boiling point elevation. So since freezing and boiling points are colligative properties, they depend on the amount of dissolved solute in solution. So we can find that the change in boiling point temperature is equal to the constant Kb, which is a constant in a table that gives you the constant for changing the boiling point. So lowercase b means boiling. So you look up whatever solvent that you're dealing with. So again, this is a solvent. Okay, so for aqueous solution, we're dealing with water. So a change in boiling point temperature is equal to Kb for water times lowercase m, which is our molality, which again is going to be our moles of solute, over our kilograms of water, times our Van't-Hoff factor I. Likewise, our change in freezing point, so T sub F talks about changing freezing temperature, is equal to negative Kf, so again we find Kf for water, times the molality times the Van't-Hoff factor. And the reason that we have a negative sign there is that it's freezing point depression. Okay? And this Kf term are positive, molality is positive, Van't-Hoff factor is positive. So in order for that to be a depression, so a lowering of our freezing point, we need to have a negative sign in that equation. So one last thing to note before we finish this video here, these are delta temperatures. So delta means change. So change, so if we talk about delta Tf is equal to the temperature of our solution minus our temperature initial. Okay? So if we have a freezing point depression of water, so say we start from a 0 degrees Celsius freezing point, and then our temperature of our solution ends up being a 2 degrees, so minus 2 minus 0 would give us a delta T equal to negative 2, which would be a freezing point depression. Okay, so if you're trying to find out what the new freezing point of a solution is, you would rearrange this equation to solve for T solution. So if we bring it over here for some more space here, you would say that the temperature of freezing for our solution would be equal to our delta T sub F plus the temperature initial. Just rearranging this equation. All right, that's it for today's pre-lab lecture. We'll see you in lab.